Accelerating polysilicon verification coverage with transaction sequence modeling. Then, abstract. The design verification is a crucial stage in the development of the integration circuits and employs simulation-based techniques to identify the rectifying the design errors early prior to the silicon implementation, thereby serving a resources through a shift-left strategy. Universal verification methodology UVM is a standardized framework used by DV. UVM transaction sequences define the simulation that is executed as part of the DV test case. This paper presents a method that uses UVM transaction sequences to train machine learning models that predict the likelihood of the hitting a code or a function coverage item. These models are then used to assess if new UVM sequences will increase coverage, and simulations are run only if an increase is likely. This approach saves time and resources by avoiding simulations unlikely to boost coverage, ensuring efficient resource utilization. This technique was applied to the coverage of two designs under test DUT. The results demonstrate the transaction sequences can be used as an input to train machine learning models to predict code and functional coverage. Additionally, the results show coverage acceleration for one of the DUTs. Introduction. Design verification (DV) is a vital phase in the life cycle of an integrated circuit in product development. So it primarily employs simulation-based testing, which, despite its popularity, is not time-intensive and demands substantial engineering resources. The primary object of the DV is identify and rectify design flow at the earliest stages, preferably before the silicon implementation. This shift-left approach helps to avert or at least mitigate the expenses associated with the late stage both detection and resolution. Coverage, both code and functional, is a standard metric in DV used to quantify the extent of testing performed on the design. Performing exhaustive testing on the industrial design to achieve full coverage is generally infeasible. The constraint random testing (CRT) is a technique used in DV to generate a limited and but wide range of test scenarios by applying a specific constraint to random input, selecting tests and more likely to increase coverage and running the simulation only for those test optimizes machine time, so reduce the verification duration and potentially improve the coverage metrics. We use the term test to refer in CRT terminology to a single run of a flavor of a specific seed value. A flavor refers to a specific set of constraints applied to a randomized data, essentially defining a particular variation or pattern within the wide range of the possible random inputs. Description. The method presented in this paper identified whether a set of transactions that a test case is about to execute as a simulation is likely to increase coverage or not. If the set of the transactions pertaining to a test case are determined not to increase coverage, then the simulation is not run, thereby shortening the verification time. Universal verification methodology (UVM) transaction sequences. Representing a test case are used in train machine learning (ML) models, which are designed to predict the likelihood of covering a code or a functional coverage item. These trained ML models are used to assess whether a new set of the UVM sequences would likely result in increased coverage. The new set of the UVM sequences are generated as part of the regular constraint random-based DB flow. The actual simulation is only continued if the coverage is likely to increase. Given the simulation can be time-consuming, Avoiding those unlikely to boost coverage leads to significant saving in time, as well as machine and machine engineering resources. The strategic approach ensures the efficient utilization of all resources. Each transaction sequence can be visualized as a 2D matrix where the columns represent a field of the sequence, for example, buffer ID, a key, and etc., and each row corresponds to a timestamp. The two sequences were first merged based on the timestamp of the time items in the sequence, this shown in figure 1, and each field was represented in binary form, expanding into as many columns as there are bits in the field. For example, an 8-bit field results in 8 columns, additionally 8 columns. So additionally, a binary column was added to indicate whether items originated from the write sequence or the read sequence. So the 2D matrix was flattened into a 1D vector by concatenating the rows of the matrix in order. Thus, each test generated one 1D vector and a corresponding output label for a given line and a cover point, and forming one sample in output pair. So there is a figure 1 is the example transaction sequences shown here as a write and a read sequence. The timestamps are used to merge two sequences. An additional column is added with an entry of 0 for a write and 1 for read. Write transaction sequence, read transaction sequence, and the merged transaction sequence like that here. Next is the transaction sequence modeling methodology. There are two phases in the application of this methodology. The first phase, the full simulation alone, and UVM transaction sequences and corresponding coverage data gathered, and the machine learning models are trained from the gathered data. And in the second phase, the trained models are applied to the UVM transaction sequences generated as part of the test. That is, a single line of a flavor of a specific seed. To decide whether to run the simulation or not, imagine that a test or simulation run consists of 2 parts: generating sequences and then the running simulation only if the sequences are deemed likely to increase the coverage. The phase 1, train. Figure 1 depicts the steps involved in phase 1. UVM transaction sequences are generated as part of the regular constraint in random testing. So simulations are run and coverage metrics are collected for this simulation. The corrected transaction sequences and coverage metrics are used to train machine learning models as gradient boosted models. For example, XGBoost and Light GBM and the neural network models. The transaction sequences from the input to ML models and the binary coverage for a specific line or functional cover being is the input. Transaction sequences can be composed of the different fields were selected based on having a variance above the threshold. For example, 80%. Fields were either integer values or categorical, and integer value fields were converted to the binary vector. Categorical fields were converted into indicator variables. Fields were stacked horizontally, and multiple transaction sequences, for example, write and read, were interleaved based on their timestamp. When multiple transaction sequences were used, only field common to both were used. The ML task is classification. Models that meet a minimum performance criterion. For example, based on the area under the curve AUC or the other ML metric threshold are retained. The criteria for ML models that are retained is a trade-off cover bins. Hence, the criterion can change from the application to another. For example, retrained models are very low and AUC leads to more simulation being performed. Conversely, retaining only models with a very high AUC area under the curve could result in too few simulations, potentially missing certain hard-to-hit lines or functional coverage bins. The trained ML models are saved for the later use in the phase 2. As more tests are run over time as the power of the DV process, the trained ML models may be updated or retrained from scratch. B. Phase 2. Apply. Figure 2 depicts the steps involved in phase 2. When running a test case, transaction sequences are generated as a first step using existing DV test. The DV tests are typically the constraint random test, signal constraint, if any, are applied prior to the generation of the test sequences as part of the constraint random verification setup. Before the tests are simulated, the transaction sequences are input to the previously saved trained ML models. For the transaction sequences for each test, the models are used to predict coverage of the test target line or a target functional or cover bin. For a single line or a target bin, the ML model prediction are used to determine the simulation is to run or not. If the transaction sequence for a test is predicted to likely not increase in coverage, then the simulation for the test is not run, saving simulation time and the resources needed to run a simulation. If there are multiple lines and functional cover bins to be covered, the coverage presented in the form of a binary coverage vector. The total coverage is the sum of the elements of the vector. The given budget of the case simulation, n with the n is very greater than k, sequences are generated. The figure 3 is a state transition of a lock DUT, and state 3 is on lock status. State. The n sequences are ranked and k of selected. The ranking and selection strategies would be based on what works best for a given DUT. And depending on the DUT, many strategies are available for picking the A sequences, including A. Picking the top K sequences by the total coverage. B. Picking the bottom K sequences by total coverage. C. Combination of A and B and D selecting K sequences based on whether the predicted coverage includes or does not include the instance of a path of existing leading to uncovered item. E. Maximizing diversity by the selecting K vectors that are as different, for example by Hamming distance, from each other as possible, and etc. Result. Lock DUT. Lock DUT is a register transfer level RTL design that will set a sequence of code and locks only if the sequence matches the predefined pattern. Many lock DUT variations are possible. The state transition diagram of one such variation of a lock DUT is shown in figure 3. The bit width of transactions for this lock is 8. The maximum number of transactions is also set to 8. So the line corresponding to L3 can be reached only if the code 0xCC is received after previously first leaving 0xAA and then receiving 0xBB in that order among the previous transactions. For example, the sequence 0x11, 0x11 and 0xAA, 0x22 and 0x33 and 0xBB and 0x44 and 0x55 and 0xCC. All the sequences 0xAA, 0x23, BB, CC would unlock the DUT and cover the L3 line. The DUT poses a significant coverage challenge, more so if the bandwidth of the code is large. For example, if the maximum number of transactions are 3 and the bit width of each transaction is 8 bits, the probability of unlocking the transaction sequences generated uniformly and random is 1 in about 16.8 million. If the maximum number of transactions is 4, and the probability is 1 in about 5.8 million. An XGBoost ML model is trained to predict coverage of the line corresponding to state S1, phase 1. Each input was a sequence of a length length 8 of 8, and the corresponding out label was 0 or 1, depending on whether the target line was covered or not by the sequence. The model was trained on the 10 kilo transition sequences generated uniformly at a random of 70 and 30 training validation split. In phase 2, more transition sequences of length 8 was generated uniformly at random, and each of these sequences were input to an ML model, which predicted if the transition sequence would cover the line corresponding to state S1 or not. Then the simulations would only follow those sequences for which ML model predicted would hit state S1. For a code length of the 8 of a sequence length of 8, about 366 kilo, random simulations are needed to average to lock the DUT. Using the method described in this paper, about 200 and 2,002 kilo simulations of average were needed to unlock, resulting in a 18 times coverage acceleration compared to the random simulation. This step is in figure 4. So this figure 4 is line coverage acceleration compared to random simulations for the Lock DUT. And the next one, table 1, result for the coverage of the cache DUT. Our model was trained for each line. A line is unique, and so the line number, the last column percent test is the percentage of the test that cover the corresponding lines. Models for many lines have high AUC values, demonstrating the excellent predictive performance for those lines. So the table 3 is about the B, cache DUT. Cache DUT is a Micron internal RTL design written in Verilog for confidentiality regions. Information about the DUT is not shared here. The design can be conceptualized as being composed of multiple models. Each module can be instantiated multiple times, meaning of a module can be several instances. A coverage line is uniquely identified by an instance and by a line number. When a set of the tests are run, if the none or very few of the tests cover a line, that introduces enough new data into the model line. On the other hand, if all or most of the tests cover a line, then it's not interesting since it is already covered. Hence, for all the coverable lines in the design, lines that covered by 10% and 90% of the tests were chosen to be models. Several tests were run as a part of the regular DB flow. The test bench was inserted to save the transition sequences. Each test generated two sequences, one for write commands or one for read command. Coverage metrics were collected for each test, then for each under consideration on XGBoost and Light CGBM and other models were trained for the classification task using the corrected transition sequences as input and the coverage that lines as output. For a given line, the ML models with the highest AUC was retained as the best models. In the cases, either XGBoost models of the Light GBM model was the best ML models. So additionally, for comparison, we trained the dummy classifiers, and the dummy classifiers always resulted in an AUC near 0.5 is not shown, 0.5, and is not shown in the result. So the table 2 is a result for the functional coverage for the cache DUT. A model was trained for each cover bin, and the cover group consists of multiple cover points, which in turn contain multiple cover bins. Models for many cover bins have high AUC values, demonstrating excellent predictive performance for those cover bins. So here is table 1 is represent the result of the best ML models aggregated by modules in the DUT. The AUC area under the cover is a standard ML metric that is ranging from the 0.5 to 1.0 and with higher levels indicating better performance. Lines with a high AUC, for example greater than 0.9, are selected for the next phase. It can be observed that many lines are well models. AUC close to 1.0 while others are not modeled effectively. IUC closest to 0.5. Table 2 shows the region of the MM model segregated by functional cover groups. The functional cover group contained multiple cover points, which in turn contain multiple cover bins. Like line coverage, only bins that are covered by 10% to 90% of the tests were chosen to be models. Models for some of the bins performed well and chosen for the next phase. About 28% of the functional cover bins have a high prediction performance. Summary. This work shows that the transition sequences can be used as an input to train machine learning models to predict code and functional coverage. This work also demonstrated coverage acceleration using a transition sequence models. We showed the transition sequence modeling for the two DUTs, Lock DUT and Cache DUT. The line coverage was predicted for both the Lock DUT and the Cache DUT, and the functional coverage was predicted for the latter. For the Lock DUT, we used the trained models to select transition sequences to run the simulation. So compared to the random simulation, our method achieved the 18 times acceleration. So there are so many references, constraint test, IEEE, and the XGBoost, right to BGM, and the categorical values, and the classification, and the other scikit-learn dummy classifier segmentation about that. Okay. Today I read this paper, Accelerating Polysilicon Verification Coverage with Transition Sequence Modeling. Thank you for your time. See you next time.